The other features here, and therefore we must make sure that it has a correct near wall behavior. It has to go back to y raised to 4 behavior in the near wall zone. So what do we do is simply we introduce a damping function. Okay, so since the modeling behavior, since the near wall behavior is different, note here the near wall behavior of exact and modeled term, or the term that we used is modeled turbulent diffusion. Exact and modeled turbulent diffusion, the near wall behavior of exact and modeled turbulent diffusion terms are different. So the suggestion is to introduce a damping function which will have 1 over y behavior, so that it goes back to y raised to 4 behavior in the equation. So where do we introduce this damping function? We essentially introduce it in the eddy viscosity term, because that is what is coming in the modeled equation here, nu t by sigma k dou k by dou xj, right? That is replacing this entire triple velocity correlation term. So we introduce a damping function, okay, for the eddy viscosity term as something called f mu is your damping function, which will have a y raised to or 1 by y behavior. You should note here the damping function should be non-dimensional, because every term in the modeled equation is consistent dimensionally, right? So this nu t by sigma k dou k by dou xj is, its dimensions is same as in the exact term. So damping function should be non-dimensional, and yet it should recover the y raised to 4 behavior in the near wall zone. Okay, so we introduce this. However, f mu should be non-dimensional. So that modeled equation remains dimensionally consistent. Consistent with exact equation. So we don't change the dimensions, that will become incorrect. So one option of introducing a damping function is to relate it to what is called using this again what is available to us, which is k and epsilon. Using that we can introduce a function. There are many damping functions available. One option is to use f mu can be exponential of minus 3.4 divided by 1 plus RT by 50. This is squared. This is one of the damping functions that is used in Launder and Sharma, where RT is computed as k square by nu epsilon. So it's dimensionally, this is the only term that is introducing a parameter, so it will be non-dimensional. RT is non-dimensional, easy to see. This is K is meter square by second square. So the square of that, meter raised to 4 by second raised to 4. Nu is meter square per second, epsilon is meter square by second cube. So this is non-dimensional. So F mu is, this particular reference for this is, reference is Launder and Sharma article. Okay, so this particular thing can be introduced, and where do we introduce? In the eddy viscosity. Okay, so what does that mean is that you need to have something called mu T LRN. Eddy viscosity mu T LRN must be introduced, which is F mu C mu K square by epsilon. So nu T LRN will replace nu T, eddy viscosity, throughout. Wherever eddy viscosity is occurring, this is introduced, the damping will become y raised to 4, or it will not y raised to 4, it will just reduce one extra y dependency in the model equation, right? It essentially F mu has 1 over y dependency. Now we have seen only the equation for the turbulent diffusion, right? So there is another term that we have not seen here. So this particular term is taken care of. This one is done, right? So there is another model, another term that is modeled, which is the your Reynolds stresses here in the production rate and the in the model equation using bussiness. So we must see whether these two have same behavior or different behavior, and whether it requires nu T LRN. Okay, to our luck, nu T is appearing here. So if the behavior is different, same nu T LRN will work. I don't need to do anything, simply replacing nu T by nu T LRN will work also for this. So before that, let's go and see what is the behavior that I get for these two production terms, right? So this is the diffusion is done. Now let me just go and see here. Production rate, right? So the PK. So the PK exact is, you have minus ui prime uj prime over bar here, and of course you have this dou ui bar by dou xj term is also appearing, right? So dou ui bar by dou xj. So this will give me sum of 9 terms here, but dou by dou x1 and dou by dou x3 terms are again 0. So this essentially reduces to minus, so j has to be 2, so it's ui prime u2 prime dou u1 bar by dou dou ui bar by dou x2. Since dou by dou x1 of the statistically average term and dou by dou x3 of any average terms are 0, statistically homogeneous in x1 and x3. So only x2 term survives here, dou by dou x2 of ui bar, which if I expand, I get sum of 3 terms, which is minus u1 prime u2 prime dou u1 bar by dou x2 minus u2 prime dou u2 bar by dou x2 minus u3 prime dou u3 bar by dou x2. Again u2 bar and u3 bar, these two mean velocities are 0 for a fully developed flow. Fully developed, right? So only one term is surviving. So I can write this particular term consistently with your XYZ formulation. If I use it, I get minus u prime v prime dou u bar by dou y. This is your pk exact, reduces to this particular term now. And what does this give? What is u prime? U prime has y square, sorry, u prime has, let's go back and see, u prime and v prime. U prime has y behavior, v prime has y square behavior. Okay, so this will give me y cube behavior, u prime v prime average dou u bar by dou y. U bar or u instantaneous or u prime will have same y behavior as u prime. We have not done the Taylor series expansion for mean velocities, but if I do it, I get the same thing. I expand, apply the boundary condition, I get the same near wall behavior. So u bar and u prime will have y behavior only, y dependency, right? So that means dou u bar by dou y will give me, so that means I have only y cube behavior for the pk exact. Okay, so now let's see what is pk model. So pk model, we used the Boussinesq, which is 2 nu t Sij, which is dou ui bar by dou xj plus dou uj bar by dou xi, 2 nu t Sij minus 2/3 k delta ij dou ui bar by dou xt. So I essentially get this particular term. We have already expanded this once long back when we did the model constants. So if we quickly recall it, it is essentially going to reduce to a very small term. So we essentially get nu t dou ui bar by dou xj square. So I get square of this plus nu t dou ui bar by dou xj dou uj bar by dou xi, the cross term here, and then I have minus 2/3 k delta ij dou ui bar by dou xj. This particular term goes to 0 when delta ij is 1. That means I equal to j. Because of continuity, this will go away. Due to continuity, this term goes away. Only these two survives. And if you expand all these terms and apply this statistically homogeneous as well as the fully developed condition, you will see that all these terms are vanishing. We have done this before, but if you quickly do it, it's dou, I'm going to take only dou by dou x2 term, because dou by dou x1, dou by dou x3 term I drop, dou by dou x2, and then I will have, this is square term, right? So I and I are repeated, this particular term, so I get ui bar dou ui bar by dou x2. Only this particular term is surviving here, plus here I have nu t of, same holds good too, so I have dou ui bar by dou x2 dou u2 bar by dou xi. Okay, so u2 bar is 0, so this is 0, fully developed. So this entire term goes to 0, the last one is 0. So I get this is now equal to nu t of dou u1 bar by dou x2 whole square plus nu t dou u2 bar by dou x2 whole square plus nu t dou u3 bar by dou x3 whole square. Again u2 u3 fully developed condition, this 2 goes away, making this only one term remain here. Okay, so I get pk model is equal to nu t dou u bar by dou y whole square. So this is what I am getting now. So what is the dependency here? So if I look at this, nu t is c mu k square by epsilon dou u bar by dou y square. So this will give me k square y raised to 4, okay, y square y raised to 4 behavior. Epsilon has no y dependency and dou u bar by dou y will have no y dependency again, squared. So that is essentially giving me y4 behavior. So let's compare the exact and the model term. The exact term has y cube behavior, model term has y raised to 4, and there is an eddy viscosity term luckily. So nu t LRN will have 1 by y behavior, making it y cube behavior, right? So I can simply introduce nu t LRN, okay. The nu t LRN can help here. We can have nu t LRN will correct the near wall behavior. And make it y cube like the exact. Okay, so epsilon I don't have to do anything here. In the previous if I compare equation 1 and 2, these two are the only model terms, rest are all similar. Epsilon is this is the exact expression for epsilon. We have just solved a transport equation for it, we did not model that. So nu t LRN will help you, give you correct near wall behavior. So in a Low-Reynolds number model, use a damping function, and you need to also use the correct mesh guidelines. So by merely having lot of grid points close to the wall does not mean you will get the correct model behavior. You must use the damping function also, okay. Just because you are capturing the near wall data doesn't mean that it should be good. It may give a wrong data unless you damp it correctly to account for 2 component limit. Otherwise the prediction will be much different than what it should be, okay, fine.